Okay, I'd like to go through what's known as convergent series now with you. So what we're looking at here are geometric sequences whose terms get so small. So let's have a look at an example here of a divergent series perhaps. So if we start with 8 and we add, let's say we've got a common ratio here of 1.5. So the next term is 12. And then the next term is what are we saying, 18. And then we're saying it's 27. So we've got a common ratio here of 1.5. Now what's happening is that if we go and have a look at the sum of this, and that's 8 plus 12 is 20. That goes to 38. And we're adding, that's 47. Now these terms are just getting larger and larger, and our sum is getting larger and larger. So this would be a divergent sum. We can't ever. It's diverging. It's getting larger and larger. It's not closing in on a particular value. So that's divergent. The opposite of convergent. In fact, if we were to look at the graph of this, if we're looking at what this represented in terms of an nth term rule, then that would be 8 times, what would it be? This is 1.5 to the power of n, and that would be from starting value of n equals 0. And so if you had a look at graphing that, 8 by 1.5 to the power of n, then you'd be looking at an exponential series that kicks off at 8 there. And so so this will be picking up the terms, and it's just getting larger and larger. So what we end up with here is, okay, that's divergent, and that's so for r equals, now if we picked up here that r was equal to 1.5, okay, make that note. Let's say that we take another sequence and we look at smaller values. So what we're doing is we're still looking at a geometric series in terms of its being a sequence where we're finding the sum of the terms. But now we're going, and let's see, our common ratio here is 1/2. And what's happening is the terms are getting smaller and smaller. And we just do a bit of that. And if we have a look at the sums here, 8 and 4, we've got 12, 4 and 2. So we're just adding as we go here, 15. Now we've got 15.5. Add another quarter, that's 15.75. Add another eighth, and I don't know where we are. We're now at 4/8, 6/8, that's 15 and 7/8. If we go to that, and if we turn it into 16ths, we're now at 15 and 8, 12, 14, 15 16ths. And if we add this on, we're now at 15 and 31/32. So you can see what's going on here. We're just going to be just short of 16, aren't we? So this is a converging sequence. This is a convergent series because it is the sum is converging on, it would seem, 16, but never quite getting there. It's sort of like this. It's like this theory of, or this principle of, if we start here, and this is a wall, okay, we're just jumping towards this wall. We're going to take leaps towards this wall, and what we're going to do is we're going to measure the distance between me and the wall, and I'm going to jump half that distance. Actually, you don't jump that way, do you? You jump that way. Okay, so I'm now here, and I've jumped half the distance from me to the wall. Now that distance is whatever, x. I'm going to jump x over 2, so I'm now going to end up here. Got smaller 2 in the process, and then we go to here and here. So now we're here. We jump half the distance each time. Keep on jumping half the distance, and what happens is we never quite get there, do we? Because we're always halving the distance. So that is what is happening here, and here is the same kind of concept of a geometric sequence where our common ratio is a fraction, or more specifically, is less than 1. So it converges because it's a convergent series because r is equal to a half or more. It doesn't need to be a half. If it was a third, we would find the same thing. If we take a 6 and we add 2 and then we add 2/3 and we keep multiplying by a third, we're going to get another convergent series where try again. We've got 8 so far. We've got 8 2/3. Right, now we turn it into ninths. It's 8 8/9. Now we turn it into 27ths, and if you work that through, that's 18, 24, 26, 27. So 8, 26, 27ths, and you can see what's happening. So this is another convergent series where r is equal to 1/3, and what we would say is, if I can get my pen up, what we would say is that the sum is converging on, what would we say, 9? It's converging on 9, and up here it's a convergent series, and the sum is converging on 16. Okay, so we can generalize and we can say that, in fact, if we have a geometric series and the common ratio r is in fact, what I'd need to say is r is between -1 and 1, and the common ratio lies in that range of values, then the series is what we call convergent on a certain value. So let's have a look at, well, we've looked at a couple of examples and we can see what's going on, but let's see how we can perhaps develop this into a formula. So we know that now we know that the sum to n terms is equal to u1 by 1 minus r to the n over 1 minus r. Okay, so now for n equals infinity, so we're looking now at an infinite number of terms, a never-ending number of terms, if you like. I have a bit of a problem saying n equals infinity. For n approaching infinity, might be a little more acceptable. And r between -1 and 1, what we're going to have is, n is equal to infinity, so the infinite sum will equal u1 minus, 1 minus, now this r to the n, let's think about this, r to the n, when r is a fractional value and n is infinitely large, that is going to go to 0 as a value. So what, just a little point of explanation here. So as n approaches infinity, r to the n will approach 0. So we're looking at values, if you like, put in your calculator, half to the power of 100, and it's infinitesimally small. So r to the n is going to go to 0 as we consider large values of n, which is exactly what we're doing on convergent series. Okay, so let's just simplify this then. So this value now is 1, so what we end up with is just the first value over 1 minus r. That is our convergent sum formula. So our example, our EG. Okay, so I've just put an example up. So for the geometric series 8 plus 4 plus 2 plus 1 plus a half, etc., find the convergent sum, or sometimes this is called or infinite sum. Means the same thing. So right, let's work this out. We know. Oh, this thing's killing me. We know that u1 is equal to 8, r is equal to 1/2. So my infinite sum being u1 over 1 minus r is equal to, in this case, my u1 is 8. 8 over 1 minus a half, which is a half. 8 divided by half is 16. Now this is what we suspected up here, converging on 16. So we've put that into some sort of theoretical context and justify that result. If we have a look at the second example here, where r was equal to 1/3, that was this one here, starting with 6. So we had u1 is equal to 6, r is equal to 1/3, and our infinite sum was equal to the first term over 1 minus a third, 6 divided by 2/3, which equals 9, which matches our result here. Okay, so one more example. Okay, just as a final example, I want us to evaluate this sum here, represented by this sigma notation for n equals 1 to infinity. So, in other words, the infinite sum, the convergent sum, my r is equal to minus a half. We can pick up from that. But let's just write out the first few terms anyway. N equals 1 goes in here, we get our power becomes 0, so we get 1. N equals 2, we get 1 in our power, so minus a half to the 1 is minus a half. N equals 3, it's 3 minus 1, 2, so minus a half squared is plus a quarter. When n equals 4, it's cubed, minus a half cubed is minus an eighth. So we can see what's happening here, and so my infinite sum is the first term, which is 1 over 1 minus a half, which is equal to 1 over 3 over 2, which equals 2/3. Okay, that's enough for now. We can get on now with exercise 1D when we get to class tomorrow, and then also exercise 1E. Plenty of work to do. I'll see you soon.